Dear colleagues, I greet you from Slovakia. Due to difficult circumstances, I was unable to come to Zagreb, and I would like to thank the organizers for the opportunity to present this remotely. I am going to focus on our experiments with algebraic differential cryptanalysis, which were done by my master student Alena Bednarikova. This talk will start with a short introduction based on algebraic cryptanalysis, then we will move on to how algebraic differential cryptanalysis works, and then, based on these introductory parts, I will explain what is the change in our new method and present our experimental results. So what is algebraic cryptanalysis? Suppose we have a single plaintext ciphertext pair. These two values relate by some unknown key and encryption algorithm, and if we rewrite this fundamental equation as some system of small equations, we can hope to find key k from the system of equation by solving such a system with a solver. In general, this is a very difficult problem, so we can only hope that cipher has some flow which allows us to solve this kind of system of equation, or use it on a small model to extrapolate how difficult it would be to solve some larger system. Thus, in our experiments, we focus only on a simple cipher model, small substitution permutation network, with equations represented as Boolean predicates in conjunctive normal form, CNF. We then feed this CNF into crypto-miniset in Sage package, and from the Boolean predicates we expect that it is satisfiable, and the substitution of variables will give us a key to the substitution permutation network. And we are interested how long does it take, and whether we have some false solutions, or whether we have a unique solution. Our substitution permutation network is very simple. We take plaintext, feed it into layers, S-box layer, XOR by the key. In each layer there are 4 S-boxes. Then there is a linear layer, which in our case only a simple permutation of bits, like the first bit goes directly to second S-box, and so on. And then this is repeated in 4 such rounds. It's very simple. It's 16-bit plaintext and 16, 32 or 80-bit key, depending on our model. Unknowns in our systems are key bits and all S-box inputs and outputs. The equations are prepared in the form of predicates. There are predicates for S-boxes, which this is the general form, and predicates for linear parts. Crucial is to model S-boxes. We based predicate P1 on the following table. For example, if S-box changes 0000 to 0001, we assign it true value, and all other options of x0 is false. Then we encode this in some conjunctive normal form. So these false points represent clauses, but essentially this will get simplified by merging some of these clauses together. And then we feed the whole system into a SAT solver, and the SAT solver will find a solution with some key values, which we then read true is 1 and false is 0. If we somehow are able to obtain multiple PC pairs, we can also use it in algebraic cryptanalysis by preparing multiple equations or multiple systems of equations or predicates by assigning the same key variables. So we have multiple such systems of equations, but we have different variables for SBox's inputs and outputs because they are independent in some way, but we have the same key variables. Essentially, the number of PC pairs corresponds to number of such systems, thus the system size grows linearly, and this means that it gets slower and slower to solve the system. Even if we have more information about the key, typically it takes longer to solve the larger system. Thus, if we have a very large number of PC pairs, we should instead use some statistical properties instead of algebraic properties. And the statistical properties typically we can use for differentials, or how the system behaves if we make some change. For example, we change one bit in the plaintext, and we focus on how this difference is spread in individual rounds. And if we can find some characteristics with high differential probability p, we can try to exploit the characteristic. There are multiple techniques how to do this, but we will be focusing on algebraic differential cryptanalysis, which is essentially a combination of this differential and algebraic attacks. So what we will do is we'll prepare an equation system for one PC pair, encrypt P1 to C1 by K, and for some second PC pair, encrypt P2 by K to C2. And now this plaintext and ciphertext have some suspected difference with some probability p, and we can add some linear equations between these plaintext, ciphertext bits and some internal bits, depending on expected differences during the encryption. Thus we have a system consisting of one equation for one plaintext, ciphertext pair, second equation, and some linear equations, and we can try to solve such a system for each two PC pairs essentially, and check whether there is a solution. And this solution only exists with probability p because we have added these linear equations. Thus we repeat this many times until the system is solved. And the method is successful if this repetition is less costly than computing key from just a single pair without this extra information. This algebraic differential cryptanalysis was known for a long time, but we have been looking at the representation, and you essentially see that for each suitable differential characteristics we need two algebraic equations for dual encryption and linear system, but we have looked at it differently. Why should we use two systems of equation and extra set of linear equation? We can try to look at the single encryption and try to incorporate a new information from the differential characteristic, and where we incorporate this is into the S-box part. So we modify the predicate P1 to P1 prime essentially by adding extra information to this basic part, and this extra information goes from the expected difference on the given S-box. So we suppose the delta x on this S-box led to delta y, and we add this information to the predicate describing the S-box. This is the way we do it. We fix some input and output difference, and check if x is 0, y is supposed to be 1, 1, 1, 1, 0, and if we change x by delta x, y is changed according to delta y. So we leave this x, y, and this as well, these two as well. On the other hand, if we try this with x 0, 0, 1, 0 and change it according to delta x, then if we change delta y, then this change is different from this fixed delta y. Thus, we will cross out this assignment, and instead of in original method there was true, his will be also false. Thus we essentially simplify the S-box to contain only some possible x values and corresponding y values, depending on the chosen difference. This means in our new method we will have, instead of two nonlinear equations for encryptions and linear equations, only one system, which is even more simple. Let's take a look at the experimental results. In the first experiment, we can see that algebraic differential attack is much faster than standard algebraic attack, regardless of the S-box choice. And if we extend this, we can also see that if we use full difference, the attack is much faster than truncated version, where we only use differences in the first and the last round for algebraic representation. The more information from differential we use, the faster the algebraic part is. Fortunately, this means that there is a slower probability of finding such a pair than in this case, and this is essentially can be used on any pair. So we have a trade-off between probability and the speed of algebraic attack. We will come back to actual total time. Further, let us compare the original algebraic differential attack, which is our aid method, with our new representation. These are these two lines, and we can see that our new method is significantly faster in case of truncated difference, and gets worse with more PC pairs, and our method outperformed original method for full differences in every case. What is also interesting is the situation. The previous graph was describing situation when we have some number of PC pairs which are valid, which have a required difference. In this case, we have number of PC pairs which do not have the difference required, and you can see that it's much faster to reject such a pair, but not with our method and a small number of PC pairs. This comes from the curious situation when we are averaging essentially the time to solve the system and time to reject the system. In these cases, some systems were not rejected, unlike in Albrecht method, but were solvable. Essentially, even if we do not have an exact required difference, we chose such a representation that some pairs are still valid and produce the key, because we only incorporated some differential information and did not restrict it to the exact difference. Later, where the exact difference match is required, then we only reject pairs and our method is faster than Albrecht A even in average, because there are no solutions. Thus we can say that our method is in some way better, and if we take into account the probability, we can see that the base method is algebraic truncated differential method, which outperforms algebraic differential method and only algebraic method. In this case we use 2 PC pairs. If we extend it to 4 PC pairs, we need probability p square to find such a pair of PC pairs, and then algebraic differential method are much slower because of this squared factor. In hypothetical situation, then we can somehow find 2 such pairs of PC pairs, so 4 valid pairs with just probability p. This would be much better. So to summarize our result, we can model our PC pairs with expected difference with an equation system that focuses on single such PC pair and modified X-log equations, which leads to faster representation for algebraic differential cryptanalysis. It can be generalized to more methods than just Albrecht 8. It can be used to model truncated differentials as well. But our question in the research is whether it is possible to distinguish between 2 sets, one with a valid difference pair and one with no such pair. If it was possible, the algebraic differential attack would be much faster. I would like to thank you for your attention, and I hope I am currently online and can answer your questions.